Stanford University.
All right, so with that, let's start on lecture 3, CUDA threads and atomics. So we're going to continue the pattern from last time that first we're going to introduce you to some new part of CUDA, in this case atomic functions or atomic operations. And then kind of the second part, again, talk a little bit about how the hardware works to kind of give you a better mental model. You know, you don't need to know the ugly details, but just kind of so you get a sense of what's going on, you know, to the code you write. So atomics. The problem we alluded to a little bit both in the first two lectures is that you don't know when any given thread in a kernel launch starts and when it finishes relative to everybody else. So there's no way for threads in the same kernel launch, in the same grid, to communicate because they could be, you know, one of them could be before the other, one of them could be after, they could be at the same time. And so if you want to have communication between threads going on, you kind of need to have this pattern just without knowing anything else. You do, you know, part of your work in the first kind of kernel, you finish that off, you know, all the writes finish, you know that all the threads have finished, and then you start a second part. The problem here, of course, is that, well, you need to decompose all your kernels into all these multiple steps, so that's kind of really ugly, and it will also be pretty inefficient because if you have to do, you know, little work per grid launch, there's actually kind of a very small but fixed overhead per kernel launch, and so you don't want to do that. So you could say, well, I know that theoretically these threads go in arbitrary order, but I did all these experiments, and I think I figured out how they actually work on this one particular card right now. So I'm going to go ahead and just do something like communicate through memory between different threads. And so I know these two threads will communicate through this particular location in memory. Great, right? Well, no, there's this thing called race conditions. And so for those of you who haven't heard about race conditions yet, this basically is very ugly saying that basically the updates or the information from one thread, from any write, can just disappear, can be lost. So let me give you one kind of very simple example here. So you have two threads, in this example thread 0 and 1917. Oh man, it's got wrapped around. Yeah, it wrapped around. Really bad. This was supposed to all be kind of lined up. So just imagine it being lined up and having a little bit more resolution than we do on, I guess, on this projector. And so what happens is that they both want to write to the same, they both want to update the same location in memory, right? Again, just mentally unwrap it. And so that value, vector 0, index 0, starts out as being 0. And so you say, well, what can happen? Thread 0 can execute completely before thread 1917. So when you do add 5 to that location in memory, that gets decomposed in the hardware into a read into a register, add something to the value in the register, and then write that new value back out to the same location in memory. So if thread 0 executes completely before thread 1917, it reads in 0, adds 5 to it, and then writes 5 back. And if later on it reads that value back in, it's still going to be 5. So that's fine. And if then 1917 comes along and its input value will be 5, it will get 6. And if it reads it back later on, it will get 6. But of course, you don't know that this is the order that will happen. It can also happen in the inverse order. But that's not even the worst part. The worst part is they're both executing at the same time. And since GPUs can have up to like 30,000 threads running at the same time, this is very possible. So let's assume they're both running at the same time, and they both access, do the first read, access vector 0 at the same time. So they both read 0, and they both add, whatever it is they add to that initial value, but then they start to write back. If, let's say that all this happens at exactly the same speed, and then what will happen? The two writes will be racing to put a value into that particular location in memory. That's why it's called a race condition. And one of them will win. You have no clue, and you can't predict which one will win, and it will probably change from run to run. It's just completely based on, what is exactly happening in the chip at that point. So instead of getting, 6 in the end, if you wanted to have both execute kind of serially, you'll get either 5 or 1. You will not get 6. So because, the writes are of 5 and of 1. So your sum will be wrong. And you can think of, okay, this is an example for 2 threads. Think if you want to do a sum over all the threads in your kernel launch. Potentially what can happen is that 30,000 threads want to, update a value in a single value in memory. And what happens is that 29,000 of them get dropped, or 29,999 get dropped. So your results will be completely wrong. And so this is why you can't, even if you know exactly that these things are going to be executing exactly the same point in time on the hardware, you can't communicate through memory in this fashion because your updates could be dropped. So, as I said, this is not defined by any memory model, so you cannot assume that if you write programs this way, they will have any kind of reliable outcome. So to solve this problem, there's in CUDA what's called atomic functions or atomic operations. And atomic operations are exactly for this point. You want to update a value in memory. You want to do something to it. You want to add something to it. You want to subtract something from it. You want to just put a new value in there, whatever. And it guarantees that while you're doing this, nobody else messes with that particular part of memory. So the name atomic comes from it's basically unsplittable. Nobody can jump in the middle of something that you're doing and mess with the value underneath you. You're locking that part of memory down, doing a very fast update to it, and then you continue on. So, and this is natively actually supported by the hardware. So it is exposed in CUDA as these special functions called, atomic and then, whatever, add, subtract, exchange, min, max, and so on. These all operate basically in integers, except for the exchange case. And you can basically call them, they just exist in, when you're inside of a global function or device function. And I should also point out there's going to be some more in Fermi, so if you get some, then we can talk about what new goodness you can try there. But again, fundamentally, if you want to have data being combined or exchanged between threads, when it's okay that the order in which that happens is unspecified, right? You still don't know in which order the 2 threads or the hundreds of threads will execute, but at least you know that your updates will not be dropped. So let me just give you an example of how this can be used. So let's say you want to compute a histogram of some input. In this particular case, you're given an image with lots of pixels. Each pixel has a color, and you want to compute how frequently do you have each color in that picture. So you're given an array of pixels. Basically, the colors have been pre-converted into nice integers, so you don't have to deal with whatever the formatting. And you're given a second array which holds the buckets. And so you know that the values in here can't overflow what's in here, so you don't even need to do a bounds check again because we just wanted to get it on one slide. So what you do then is you read your input, each thread does, and then you call this function, in this case atomic add, and you pass it the location in memory that you want to update and what you want to do to it. In this case, add 1. So far, so good? And basically the address here again is, all right, I want to update this particular element of the array because my pixel has that particular color. And so this is going to get packaged up, and the hardware is going to make sure that while you're adding 1 to that particular entry in that array, nobody else comes and reads that array, that particular entry or writes to it. And so you know that the update will go through correctly, and in the end, you will get the correct result. Because this is an add of integer instructions, right? The final result will be the same no matter the ordering, except if you potentially you would mix adds and subtracts, and you could overflow or not overflow. But overall, except those corner cases, the results will be the same no matter what order your threads execute in, and no matter which GPU you're executing this on. So another example, so this is what basically for doing updates when you're writing, but let's say you also kind of want to share data on the input side. So another use case here is you're doing some work per input element, but that amount of work is totally variable. It basically could be 0, you could be throwing those elements away right away, or it could be a lot. You have to rehash stuff lots of time, or this is dynamic programming. You have to basically check if the result for this input was already computed, and if it isn't, then you have to compute it and update something, or if not, not. So in these kind of scenarios, you often want to have a work queue because you don't know how much work each thread will get. You basically want to balance it out, so you want to have a work queue where basically threads go and grab work, as they become available. So here, what is this thing? Whatever. You say, okay, I know my queue is somewhere off in memory here, and then I have a counter which basically says which elements in that queue have already been consumed. So at the start, that counter is 0, and as threads come in and update that counter, it's going to increment, and so you will know that when you grab, increment that counter, you're grabbing work off of that queue and then doing it, and nobody else will be doing that particular work, so that work won't get duplicated, and you also won't skip some elements in the work queue. So here I use a different function called atomic inc. Again, you're just passing a pointer, basically, and you're saying, in this particular case, atomic inc, you just add 1, and here the second argument is basically, what's your max value? If it's above that, you're basically going to wrap back around. So this is just to say that you shouldn't exceed, and you basically can check then later on. I just didn't include that part of the code because, again, the slide kind of limits you. And so when you get, you incremented the counter, you get back the old value. So let's say you're the first thread to access something. You're going to get back 0 because you're the first one. And so you go off and work on element 0. And the next thread which comes along will see that the counter is actually already 1. So it will get back 1, work on the second element, and so on and so forth. So this way you can, share an input even though the rate at which you're executing things, it can be highly variable, and you will, all consume all the work. So there's, a couple of caveats here. One is that atomics, because they have to lock down memory and because it's a very specific operation, are slower than normal loads and stores. So if you overuse them, if you rely too heavily on them, your program will be somewhat slow relative to other programs on CUDA, but they can still be very useful. And you'll see in MP2 that even if you use them pretty heavily, you can still be quite a bit faster than the CPU. The other thing is, again, if you have an atomic counter, so for the whole kind of grid, like we had in this example, because we said atomics ensure that only one particular thread is updating any location in memory, and if you just have one location, you'll have the whole machine basically queued and waiting on that one location in memory. So you will immediately go from highly parallel back to serial, right? One add at a time. So if you use atomics, think about parallelizing your data, not just your execution, right? You've parallelized your execution by writing, the CUDA kernel and saying, do this, launch a huge number of threads. But think about also about parallelizing your data, not just having a single counter, but having multiple ones. So let me kind of show you one example of this while showing you yet another use of atomics. So let's say you want to find the global max of the values from a big grid launch. So in this case, just read in the values, but in a real example, you would basically be doing substantial work beforehand, right? Get a value back, but you need to just determine if this is the global max. So then you can call this function called atomic max. Pretty much you see the pattern here. Again, you pass it a pointer to where the global max is stored and your value. And basically what this function will do, as the name implies, is if your value is larger than the value currently stored at that location in memory, it will store your value back. And if not, it will just throw it away, right? So that location in memory will get the max back. And if you actually read out the value, it also returns the value, you'll actually get back the previous max. And then you can check, the previous max was smaller than what you passed it, then you know that your value is a new global max. So, but again, you have this one value, the one location in memory which holds your global max. So a better way of doing this is, to parallelize your data, which is what we call kind of the simplest case of hierarchical deconstruction or decomposition. So instead of having one global max, you have a lot of smaller maxes. I'm not quite sure what this thing is vibrating like that. And you say for a certain number of threads in a group, in a region, and you can determine how many regions you have, and so how many threads will be going for any regional max. I'm first going to update my, compare my value against this group max, this regional max, and only if the old value returned by this function is smaller than mine, aka I know my value is the new regional maximum number, do I go and try to update the global max. Because, and this basically means that the great majority of updates to the global max will fall away, will get filtered, and so you won't have the whole machine queued up, trying to update this one value, but just a very small subset of them. And thus, the whole thing will hopefully run faster. Obviously, it depends on your input data pattern, but overall, you can basically say, as you make this number of regions larger, and the number of threads, kind of all trying to update that one value smaller, you're parallelizing your execution, you're opening it back up, because if you just have an update to one single location, even though you're running on a highly parallel GPU, you've basically forced execution back down to be serial, as bad, if not worse, than on a CPU. Does that make sense to everybody? All right. So this obviously can work for a max, as I just showed you, but it can work for lots of other things. If you want to do, a global sum, for example, right, then you can do partial sums for some number of threads, and then propagate those sums up to the global max, for example. You can do it for lots of other kind of operations. Again, it's not so much, you don't have to use exactly this pattern or anything like that. It's just that the thought of your data accesses, when you're using atomics, will go one after the other. That's exactly the definition of atomic updates. And so if you're using them too much and just banging away on one value, you're basically robbing yourself of all the parallelism that the GPU can offer. So you need to also think about, again, kind of decomposing your data structures and parallelizing your data accesses, not just your execution. And so I said that this value is better than the first version I showed you of max. In the next lecture, Jared will actually show you an even better way of doing it, including shared memory and other goodness. So this is kind of almost an intermediate, where did I go? Yeah, an intermediate step. But this is definitely better than just banging away on a single value. And in certain cases, this is actually the way you should go if you kind of can't have some of the conditions that will apply, that Jed will show you next time. All right, so overall, let me just recap again what I've just been telling you, which is you can't use normal loads and stores even if you're absolutely sure that the two threads will be executing at the same time, or maybe you should say especially when you suspect that they might be executing at the same time because of this issue of race conditions. Your updates, your data that you've just computed might completely be lost because two writes might be trying to update the same location in memory at the same time, and one of them will win in arbitrary fashion, and so all your hard work that you've just put into computing something is basically lost, and you will basically have an incorrect program basically all the time. So kind of to get around this issue, if you can use, again, atomic functions or atomic operations called through this interface I showed you, exposed in that way in CUDA, to update values in memory where it's guaranteed that only one thread will be doing something to that location in memory at any given point in time, and so no values will be lost. Things will go slower because everybody will have to wait on that one particular location, but it will not be incorrect. And again, because you now have this kind of ability to basically take a highly parallel GPU and make it wait on one value in memory, you have beautiful ways of slowing your program down, making it a lot slower than the CPU version. So think about how to decompose your data and not just your execution. Now you've written all these parallel threads, think about how that maps nicely in terms of different data access patterns and different data structures. All right, so with that, that's about all I had on atomics. So questions? Yes?
What's the minimum and maximum size of an operation? Like, can I do an atomic operation for any size of byte or
Sure.
4 bytes?
So the question was that what's the minimum maximum size, basically, and the answer is the default size is 32 bits, 4 bytes, so a normal word size. And you can also update 64 bits at a time, so double words. But that's it. You can't update, as you're passing in, you're passing in a value, and that has to be a 32-bit or 64-bit value, kind of what I can have in registers. And that will get updated. You can't say update this whole region at once.
What happens if I'm trying to atomically update 1 byte?
So if you try to atomically update 1 byte, you're basically locking down the group of 4 bytes which it belongs to. And since these functions only accept int or unsigned int or longs, you have to think about what do I have to do to only update that byte, right? So if you're doing something like an add or something, you have to think very precisely about, will I have bits carrying in and out for my addition or something like that? Or, do similar things. Question?
So why is float point atomic operation not supported?
So is the question, why isn't floating point?
It's not supported
Yes,
right
it's
now.
not. It's not supported. It will be supported, or it is supported on Fermi. We just didn't want to put it on there because, again, the current GPUs we have in the PUPS cluster, the things you're going to be writing, at least your machine problems on, if you're on your semester, your project, are not Fermis yet. So in the kind of the first couple of generations which supported atomics, it was basically simpler to just support ints. Kind of it's a very high-level answer, and to see if people actually will be using it. And then, when you see that it's actually useful, then you go in and add more hardware, because floating point is certainly more complex and needs more hardware added to make it run decently fast. Okay, other questions? All right, moving on pretty fast here. So let me turn again, so kind of to the second part, which is give you some more background on how your CUDA program actually executes on hardware. And again, here the goal is to give you kind of a 30-foot view of how things are going on, so you have an idea of what might work and what might not run that fast. Again, just kind of a mental model. It's pretty, you kind of have a simple mental model of what the CPU does. It's basically, it executes one instruction at a time on one data element at a time, and then it keeps on going. Right? And effectively, the hardware is much more complex. The same is true for GPUs, but this is just to give you, again, this simple model. And we're also going to talk about control flow diversions, which we kind of alluded to in both lectures 1 and 2, which is basically this case where you have threads which are executing together, and you hit a branch, an if then else statement. And one of them wants to take the if side, and one of them wants to take the else side, and how the hardware handles that, and what that means for performance. So kind of there were several questions in email, and also I think one in person, about thread block sizing in the first machine problem. And shouldn't you always choose the maximum thread block size to kind of have maximum utilization of the streaming multiprocessors on the SM? So this is kind of trying exactly into explaining that. So what happens in the hardware when you launch a kernel? Kind of explained to you last time that basically that information of which kernel to run with which configuration on which input data gets communicated to the GPU, and then there's dedicated hardware on the GPU which communicates that fact to all the streaming multiprocessors on the GPU. So what happens in detail is, so at the beginning of your computation, the streaming multiprocessor is sitting there doing nothing. And then the information comes down, hey, we have a new kernel to execute. And so they're going to ask, well, okay, give me work. And so as we explained to you last time, thread blocks, this programming instruction with thread block, physically it means that all the threads in the thread blocks will be executing at the same time on the same streaming multiprocessor. So when a streaming multiprocessor asks for work, what it gets back is a thread block number. Go execute, in this case, thread block 5, right? And so it takes that information, what does it mean to execute thread block 5, and it starts up all the threads belonging to that thread block at once and starts to execute them. But if the thread block can have different sizes, so if it doesn't fully fill up one streaming multiprocessor, it goes back and asks, hey, give me more work. I have more room. So it will get another thread block and potentially another one until it's fully filled up. It can't take more thread blocks, and then it will just continue to execute. And so the number of thread blocks that are executing on the streaming multiprocessor at any given point in time totally depends on A, the requirements of that thread block, which is how big is it, how many threads does it have, how much shared memory do you need per thread block. You can, the compiler knows that and communicates that, or the runtime knows that and communicates that fact to the hardware, and several other requirements and resource requirements, which we're going to talk about in basically the next week. So based on all that, this streaming multiprocessor knows whether it has room for one more or whether it's full now, and it just stops requesting work. But so, all right, so you have the maximum number. You're executing these thread blocks all as you go along. And so what happens is you're executing all the thread blocks at once. It's not like that the oldest thread block gets executed until it's done, and then the next oldest basically gets started. And so basically you have like an internal queue. If you have enough room, then the streaming multiprocessor will be executing all the thread blocks at once. But let's say one thread block finishes, so the streaming multiprocessor indicates to the global hardware, hey, I'm done with this thread block. Do you have more work for me? And in this case, yes, it does have more work, so it gets a new thread block. So you can think about the fact that how long it takes to execute a thread block will obviously totally depend on what kind of program you've written and the runtime behavior. I mean, there might be branching and loops and who knows what, which means that some thread blocks take a lot longer than other ones. So that also means that you don't know, for each SM when some of them will finish. And so what can happen is that the intermixing of which thread blocks execute at the same time is also basically totally dependent on runtime behavior and lots of internal policies of the hardware which change from generation to generation or even more frequently. So don't try to think of in terms of I want to schedule things exactly perfectly because I want to have exactly this mix of thread blocks running on the hardware, because very little things might, even if you can kind of reverse engineer that and figure that out, very small changes in the runtime behavior might totally change that, and obviously it will change from generation to generation. So I said the streaming multiprocessor, the SM, is executing these thread blocks all at the same time. But I also told you last time that one way that GPU hardware kind of gains efficiency is basically by sharing certain parts of the hardware over multiple of these small cores which are make up the streaming multiprocessor. And it's particularly that groups of threads which share the control part of their execution are called a warp. And that for NVIDIA hardware, that right now is 32 threads make up one warp. And so what this means is that threads in a warp at any given point in time, in any given cycle, are executing one instruction. Not all of them might be active, I'll get to that in a second, but they're all executing the same hardware. So the mental model you want to have is that the streaming multiprocessor, any given cycle, executes one instruction for all the 32 threads in a warp. That's the mental model. The actual physical implementation will vary from generation to generation and from different GPUs, but the same way as you can think of a CPU executing a single instruction on a single set of data and then executing the next instruction, you can think of a streaming multiprocessor as executing a single instruction for this group of threads, 32, a warp, and then executing the next instruction. So, okay, warps and thread blocks. So what's the combination? How does this work out? So what actually happens when the streaming multiprocessor knows, all right, I've gotten this thread block, and I know this thread block has so and so many threads in it. It says, how many warps does it take to run all these threads in a thread block? And so in this particular case, I'm showing on the slide, you have 128 threads, which means you need 4 warps, each of 32 threads each, to run it. So the hardware will basically cut up your thread blocks into warp sizes and assign the threads, in groups of 32 to a warp, and then start running them. And it will start scheduling them, warp by warp. And so some threads could, for example, be running quite far ahead of other ones because they didn't have to wait for some event while the other ones did. So even the threads within a thread block, they are not executing in lockstep. Basically, only the threads which are in these groups called warps are executing. They're always at the same instruction. And so one question you might have is, well, what happens if I give a weird thread number per thread block, right, which doesn't map exactly, it's not a nice multiple of 32. Well, the answer is, kind of the simplest thing you can think of is that you're going to populate one warp partially, and and some threads will not be active on that warp, and the rest will just execute however many threads are left over to complete that thread block. And so once that kind of chunking up into warps happens, once the SEM has gotten a thread block, as I said, the warps will execute will be scheduled independently. And as I showed you before, you can have multiple thread blocks on one SM at the same time. So here, this kind of diagram, this shows kind of time on the x-axis, and the colors try to indicate, which thread block these different warps belong to. So I hope you can see this all the way in the back. If not, I'll just talk through it. So in this example, basically, you can have warp 1 of thread block 1, let's say the oldest one, starts executing, and it has enough work, it has enough instructions which are ready to go, so it executes during the first 6 cycles. And then it hits some condition which makes it wait. The most common condition which makes threads wait is basically you have to read something from memory. To give you kind of an idea, that's a couple of hundred cycles of waiting basically for that request to complete. So while it's waiting, you don't want to have the hardware sitting there doing nothing. So the hardware will go, well, who else is ready to run? And it will say not, oh, I'm going to execute warp 2 from thread block 1, although it probably could do that. It just happens to pick warp 1 from thread block 2. So that will execute for a small amount of time. Then it hits some condition it has to wait on. And so it will pick yet another warp, in this case warp 1 from thread block 3. So you can see how warps from different thread blocks can be very finely intermixed in terms of when they execute and how they execute. And this scheduling is basically free. Every cycle, the hardware goes and says, well, who's ready? And based on some scheduling policies, which again are very complex and change from iteration to iteration of the hardware, it will pick somebody. So here, we first had one warp executing for 6 cycles, then another one for 2, and this third one comes along. But as you can see, then right away it switches to a 4th one, and this time actually it is a warp, a different warp, but of the same thread block, in this case thread block 3. And then it goes back to executing the warp which it was executing here, because whatever made this warp wait, or some threads in that warp wait, is now, that request is completed, and so it can continue execution. Only later will it go back to the warp which was executing first, just because it happened that this thing needed more time, for its request to complete. So again, this very simplified example should just show you that the ordering in which different parts, if you have multiple thread blocks running, how they execute is basically, you can think of it as arbitrary. And B, basically, the reason why you want to have lots of threads and, maximum of warps or thread blocks per SM is to basically not make the hardware stall, if it hits some condition where it has to wait. So the more kind of threads it has, the bigger pool of potential work the hardware can pick from, the higher likelihood that it will find work to do when something else stalls. Right? Pretty simple. So again, this is not kind of the be-all and end-all. Some people take this information and say, well, I absolutely have to maximize how many threads I have active on any given streaming multiprocessor at any point in time, that's not what you have to think about. This is just why, kind of the fundamental reason why you actually want to have, lots of threads. But you don't need to push it in terms of absolutely maximizing that number. There's definitely diminishing returns there. If you have a decent number, it will probably be enough, and you'll probably get the maximum amount of performance you can get out of the hardware. If once you have everything running and it runs fine, and you say, well, maybe I should get more performance, well, then you can look at what happens if I try to make small changes, which mean that I can get more thread blocks active or increase my utilization of in terms of the number of threads compared to the max number of threads that the hardware supports, and see if that increases performance. But it's not the be-all and end-all. Some people take it to be, but it's not. All right, so after kind of talking about scheduling, I want to just briefly talk about what happens, again, if these groups of threads which are executing together in a warp hit a branch statement. And so here the simplified code just says, all right, you have some function foo, which input is your thread ID, and that function might say that, let's say, all the even threads want to do one thing, like do A, and all the odd threads want to do something else, do B. So what happens actually in the hardware? So what will happen is, I'm showing you here is basically, at the red box, this is kind of where you're at in program execution. So right now, you're right before your if then else statement. And these arrows, each arrow basically indicates one thread in a kind of small warp. And basically, the arrows being there indicates they're all active, they're all running. All right, so you've evaluated foo, and so you go into the branch, and so some of them want to go do the if part, and some of them want to do the else part. So what the hardware will do will say, all right, I'm going to pick which side I'm going to execute first, and which side it will pick depends on a lot of things. And I'm going to basically deactivate those which will, in this case, want to do path B, let's say the else statement. And so they are basically put to sleep, zero overhead, so you don't have to worry about that, but they're just basically immediately put to sleep. The threads in that warp which do want to execute the if statement, go ahead and execute the function do A, and that takes however long it takes, right? That might be a very short function or a very long function. However long it takes, those threads are active. When they're all done, then the hardware detects that and says, oh, I also need to do the else statement. So I'm going to now put to sleep these threads which just did the if part and reactivate, wake up those threads which want to do the else part. And so those now go active. The rest is put to sleep, and you're executing, the do B function. And again, it takes however long it takes. The hardware makes sure that, even if inside of that do B function did lots of stuff, always remembers where you came from. And so at the end, when you're done, it comes back and says, all right, I'm done with this if then else statement. I'm going to reactivate everybody and continue execution. Does that kind of make sense to everybody? All right. So, what about more complex control flow, right? You don't just have simple if then else statements. So let's say you have if statements inside of if statements. Well, I didn't do the animation, but you can see that basically the idea is exactly the same. The hardware will take care of always having only those threads active which are going down a particular path in this graph, which is called the control flow graph. And you'll always make sure that when you get out of that particular branch, all the threads which you want will be back to active. So note here that if you're inside of a first if statement, and then you go in a second one, when it's reactivating the threads here to go down path B, it doesn't reactivate all the threads which were put to sleep because only a part of the threads actually wanted to do path B. So it always takes care of that, and it just reactivates you all the threads when they're all done with the whole if then else statement. So overall, you don't have to worry about thread divergence or control flow divergence for correctness. You just have to think about it a little bit for particular cases, and I'll explain when for performance. Because as you probably noted, if you just let me go back one set of slides, The number of threads active, when you're deep in some kind of deeply nested ifs and else statement, can be very low. And so the hardware, because it's executing, these groups of threads per cycle, it can kind of like compress out the stuff which is not doing anything, because the hardware is literally built to execute 32 threads at a time. So in this case, you're making pretty inefficient use of the hardware, right? You had up top, you had 8 threads active, and now only 2 are active, so you're basically only using 1/4 of the performance which is available to you. But that's not an issue, if you have these deeply nested branches kind of seldomly, or actually even more important, if the branch condition is such it's just coarser, right? So let me show you kind of a worst case, kind of just, right? If you have a switch statement and, let's say mod n, and you vary n from like 1 to 32, right, the max number, and you actually have some work to do inside of each of those cases, well, the performance will drop off from full performance of 32 threads executing per cycle on a single SM down to like 1. And but note here that this is only again the case, let me go back, if the branch condition or your switch statement really depends on the fine-grained thread ID in some manner, right? It might not be directly dependent on the thread ID. It might be just that your data happens to be organized in such a way that this is how it works out, and you can't predict that. Well, that's too bad. But if you know that you have a data-dependent branch and you kind of have an idea of what your data will be like, right? If you know that this is going to be fine interleaved, like I'm always going to do part A and then part B, you might want to think about, and this is kind of where I spend the majority of my time, right? That's always okay, but always like for performance, you only have to think about the places where you're spending most of your time in your execution. If that's the case, well, then you can think of, well, rather than doing even odd, even odd, even odd, maybe I want to do even, 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 and then odd, 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 for example, right? So that basically all the threads in one warp just happen to all fall into one group, and they all just execute one side of the branch, and they just completely skip the other, and so then there's basically no overhead. So this is, again, just something to think about for performance reasons. If you know that your code will look something like this, or will look something like this, and you have an idea of what your data or your branch pattern will question.
So basically, it's better to have like some sort of like a selection of the stars depending on the block ID and the thread ID.
For example, that's certainly one way to do it. The other idea you can have is if you are processing quite a bit of data per thread, then you could basically say, I am going to gather up work of type A and do that, and kind of remember what of work of type P I still have to do. When I have enough of type B, then I'm going to do type B. So Jared will be talking about in, I think, 2 lectures with SCAN, kind of with efficient mechanisms, how you can do things like that, for example. Question?
This sleeping of threads, this is done at runtime or at compile time?
This is runtime basis. This is completely done by the hardware based on what the actual evaluation of the branch condition is. So if you have, let me go back to the code. If you have this kind of code and all your threads just happen to go, they want to do the if part of the first branch and the if part of the second one, you will only do A, execute the function do A. You will completely skip everything else, and you have no overhead. This is just, if at runtime for any given thread, the branch pattern happens to be this way. It's not compile time. Question? So the question is, what about loop divergence in terms of, and that's a very good question. So what happens is, I didn't want to put this into the slides, but it's very similar. That basically, if you have some kind of loop where the number of iterations is data dependent, like for example, you can think of one case in MP1 where this is the case. The hardware will make sure that those threads which need to execute, one iteration of that loop will execute that one iteration, and then we'll be put to sleep. And then the threads which execute 2 or more will execute the next one, and so on and so forth. And you'll basically stay inside the loop until the last thread, has executed the maximum number of iterations that it needs, and then you will exit out. Now, this is a simplified example, right? The compiler can mix things up in ways you wouldn't expect, but kind of at the very high level, that's kind of how you can think of what happens to loops with different number of iteration counts per thread. Was that interesting? Okay. Anybody else have questions? All right. I've done that. So let me just wrap up again by saying that atomics are useful for communicating and gathering data, and they're actually also kind of where you want to use them. I thought I had this in this last slide, but I guess I changed it in the last second. Is if your sharing patterns are either you really want to compute some global value or some a value where lots of threads are contributing to it, like a sum or a max or something like that, or if the way you're sharing data is kind of unpredictable and sparse. For that, atomics are very good, even though they're kind of inherent, they have lower performance than normal loads and stores, and you need to be careful not to overuse them. If that's the kind of thing you're doing in your problem, then they're like, they're the right tool. If the communication patterns and sharing patterns between threads are predictable and dense, then, for example, Jared will talk to you about next time about shared memory and how you can use that. That's probably the best way to go. And if you have, kind of all-to-all communication, so that you're communicating one value to a different thread, and everybody does that, then probably atomics are not the best way, and actually you want to use something more like sort, or actually do have multiple kernel launches. But again, with those caveats, atomics can be very useful, and they're the only way to go if you want to kind of update some spot in memory, and your multiple threads will be writing to that, because else you can have and you will have race conditions, and you will get incorrect results. All right, and so with that, I thank you for your time. And any more questions about either the hardware or atomics?
The order of latency difference between normal emergence score versus atomic emergence.
So you're asking about the latency or the throughput of? So he's asking about the difference between a normal load and store and an atomic.
And if the order of it, right, is 10 times lower.
So that A will depend on what kind of hardware you're running on. Basically, newer hardware will relatively be faster with atomics. And B will also depend on your access pattern. So think anything about the case where you have a single value that you're trying to update to, then the atomics will be really, really, really slow, because everybody will be queuing in on that. If you had replaced that with a normal write, which will be completely incorrect, but then the writes were just like, well, okay, you can all go at some maximum bandwidth, and they will be much faster. But it's basically, it's hard to kind of give a generic answer. You can construct micro benchmarks which kind of show the best case, but the numbers kind of are improving, and for example on Fermi it should be much faster. So I can't give you a generic answer, sorry. Other questions? All right, so again, thanks for your time. I guess we're done really early this time since we ran over last time. So for those of you who haven't started MP1, please do.
Just a quick announcement. So we had a bug report about part 3 that if your kernel just returns 0, it passes our test. This is still the case, but I have a fix for it, so don't try to get away with it. I'm going to check your numbers. But yeah. So I don't know if someone submitted that, so thanks for that. Yeah. Anyway, okay.
All right, good luck with MP1, and if you have questions, email us or come to office hours with Niels or us on Thursday, and see you all on Thursday.
For more, please visit us at stanford.edu.